Okay, so thank you very much for having me. So what I will try to tell you about is this line of research I've been researching the past few years now, and that aims at exploiting the recent progress in generative modeling, so in deep learning, in order to assist the task of sampling. So I'm a researcher at École Normale Supérieure, and this work, has been done along the years with a lot of wonderful collaborators among different institutions and in different ramifications of around this topic. So I'm not going to talk about work I've done with all of them, but I will be citing some of the works along the line. So sampling, why sampling? What are scientific applications of sampling? So what I come from actually is statistical mechanics, where the idea is that we have a Gibbs-Boltzmann distribution that defines for a given physical system for which the coordinates, that can be described in a system of coordinates by values x, that is given by exponential minus beta u, where u is our predicted energy for the system given the value of its coordinates. So it can be, for example, a certain molecule, and I have a certain coordinates for all the atoms in the system. And if I have an effective theory for the energy of the molecule given the coordinates of the system, then I can try to describe the statistical equilibrium with this Gibbs-Boltzmann distribution. Now, what I think is more relevant to this audience is, of course, the case of Bayesian analysis, where the idea is that we have a physical process that generates a set of data. Given a way we model this physical process, we have a set of parameters for which we can compute the likelihood of observing this data. And if we combine it with a prior distribution on the parameters of our model, we obtain a so-called Bayesian posterior distribution that we want to sample in order to understand the uncertainty we have on the value of the parameters that the data is constraining for our model. And here the little example I'm using is actually from astrophysics, and it's like a radial velocity of a star around which is orbiting a planet, measured along time at different points. Those are the little black dots. And so we know it has to be a periodic signal, but with these few observations, we can very well see that many different periodic signals can fit those few observations, right? And in particular, if you look at the posterior and a slice of this model that includes the logarithm of the period and the phase of the periodic signal, what we're going to see is that there are islands of high probability in the posterior that are separated by seas of low probabilities. And that's really encoding the fact that there are different combinations of period and phases that are compatible with the data that we have collected for this process. And so these two examples are examples of cases where we know a target distribution oftentimes up to a normalization constant. So here I have a proportional. Here I don't know this normalization factor that we call the partition function, but we want to extract some statistical information from the knowledge of this mathematical expression of what I'm going to call the target distribution, and that I'm denoting by rho star throughout this talk. So what you may notice is that I'm particularly interested in these types of distributions that are multimodal distributions. So what do I mean by multimodal distributions? It's distribution where precisely I have islands of high probabilities that are separated by low probability regions. And so it can happen in Bayesian inference, but it also very oftentimes happen in modeling the thermal equilibrium of physical systems, in which case we talk about metastable systems. And so why am I particularly interested in this type of distribution? Well, because sampling in this case is particularly hard. So finding a way of extracting the statistical information from this target distribution is particularly hard. And so to illustrate this, I'm going to use this very simple toyish example where I have a distribution that is only two-dimensional, so you have two dimensions, and I have two islands of high probabilities for my test distribution. So the 101 samplers that people have used can be classified in two categories, and one of them is the idea of shooting largely in space and then post-processing the points that you have placed in your parameter space. So maybe this is going to be a bit confusing, but I guess for Bayesian inference, this x is theta all the time, but I'm using x as the variable I'm sampling. So this is the case, for example, of importance sampling, where we're going to use realizations from a simple proposal distribution. So here, for example, unimodal Gaussian distribution that I shoot largely in space. And then what I do is that I compute some weights that are going to rebalance the points that I've shooted everywhere in space. Using what? Using the ratio between the target probability I've wished I was sampling from and the probability density of the proposal distribution I actually sampled from. And if I do this, and if I change the relative radii of all of these points according to this weight, what I see is precisely that I'm putting a weight close to 0 to everybody that is in between in the sea of low probability, and I'm concentrating my effort on the high probability regions. In particular, when I want to estimate an expectation over, so my target distribution for an arbitrary function f, which would be defined as this integral, I can approximate it with a ponderated average, where I'm ponderating all the proposed point xi's by their weights w of xi, again, that are using this ratio. So this is a way of building estimators that have nice statistical properties. But what we can quickly realize when we look at this multimodal example is that it can be very wasteful, right? So most of the points I've used compute to draw and to compute weights on are completely not used by my statistical estimation. Their weights are 0, effectively. And this is, of course, a phenomenon that is worsening as the dimension of the problem I'm looking at is increasing. So not that good. But of course, and this results in high variance of the estimators, because the idea is that only a few points are really contributing to the task of estimation. This problem of scaling to high dimension was the very motivation to very quickly, with the appearance of the Monte Carlo methods, define Markov chain-based Monte Carlo methods, where the idea this time is to search the space with a local algorithm. So here, for example, I'm using one version of a Markov chain Monte Carlo, and I'm initializing it twice with these two chains. And now I'm creating realizations that are well focused on the high probability regions of my problem. Okay? Now, what's the issue if I'm trying to use all the realizations from all the chains and make this empirical average to estimate this expectation? Do you know? So here, in the example I've used, actually, I've took one of the two modes to be twice as likely as the other one. And here, if I'm just trusting the realizations of my two chains, I'm thinking that they are equally probable. I've generated as many configurations here than here. So actually, my Markov chain is here not converged. I need to have not overall visited everything. I need each of the chain I've lost to have visited all the high probability regions of my system. And so I would have needed to observe transitions between the two, and several of them, if I wanted to have a faithful measurement of the relative weights of the different modes of the distribution. And so this is, in practice, it yields some bias algorithms, meaning that, okay, if I were to wait an infinite amount of time, there are perfect theoretical guarantees for these algorithms. They would give me exactly what I want, but in practice, I can afford only a finite amount of time, and observing such transition is actually extremely costly. And so I'm not observing them, and I'm looking at effectively biased results. So if I summarize, I have, from the one hand, something that seems to handle multimodality, so putting realization in all the wells, but actually doesn't scale well with dimension. And on the other hand, I have something that scales better with dimension, but really doesn't handle well multimodality. So we need to go beyond those very simple first ideas for sampling if we want to tackle this type of beast of multimodal distributions. So, of course, there has been decades of research of how to do this, and it would be impossible to summarize this in a slide. But if I just give a couple of pointers, some things that are appreciated by practitioners are going to be so-called annealing methods, where the idea is to build a path of distributions that go from something simple that we know how to handle, so typically a unimodal distribution, and to bridge it progressively towards the target distribution, and then exploit this progressive bridge in order to build a sampling algorithm that is able to bring samples from the simple distribution back to the target distribution that is much more complex. So, okay, that would take a full class to describe all of these possible options, but keywords are replica exchange, parallel tampering, annealed importance sampling, or sequential Monte Carlo that rely really on this idea. Another thing that is really popular, and this is for the community that is busy with sampling metastable states, for example, of molecular system, is so-called enhanced sampler with collective variables, where the idea is that you identify in your problem so some relevant dimensions where you can project your problem in this low dimensional space, and where you resolve well still the fact that there are different modes. And then when you have this lower dimensional setup where you have your different modes, you can then drive the exploration of the entire state space among this lower dimensional system, and so force your sampling algorithm to look at all the locations in your space, and therefore forget none of the modes. But okay, that's pretty specific. Now, what I want to discuss today, of course, are so-called sampler assisted with generative models, which have started to appear now 5 or 6 years ago, in particular, which use different types of generative models. And here we will be discussing in particular the ones that use normalizing flows. I'm not saying more here because it will be the topic of the rest of my talk. So far, so good? Yes, okay. So you have not missed that there is an ongoing revolution of generative modeling with really some groundbreaking progress that has been made in modeling, the type of consumer data, text, images, and so on and so forth. And the one underlying paradigm that is important of how we build generative models is this so-called deep latent generative modeling, where the idea is that we start from a simple distribution that we call the Bayes distribution, of which we can easily obtain realizations. And then we send those realizations of the Bayes distribution through a neural net to create the outputs of the generative model. So the output of the generative model, X, is equal to T theta of Z, where T theta is a neural net parameterized with some parameters theta. And with this and modern technology, if you have access to extensive datasets to train, for example, on images, you can create realizations of the Bayes distribution that look like just an image with just Gaussian white noise pixels and transform it into an image of a nice-looking dog. And this is really defining an effective distribution, because each time you are sampling a new Gaussian random pixel image, you get a new dog at the output. And so this is what this effective construction that creates an effective distribution. I call this effective distribution rho theta of X in the rest of the talk. So this kind of begs the question of how can they be used for sampling, since here I have a very easy sampling process for rho theta. I just need to sample from my Gaussian and then send it through my neural net. And I can this way obtain IID sample, so independent sample, perfect sample from my rho theta, even if rho theta can be a distribution in a very high dimensional space. And you can imagine even a multimodal distribution, as there are different breeds of dogs. Actually, we can do one model that will generate planes as well as dogs, and so on and so forth. So how can we use this technology to assist in our problem of sampling? Well, there is 2 questions we will have to have in mind right away as we are putting on the table this program. And the first one is, okay, but I want to use generative modeling, deep learning, so on and so forth, but I still want to do science with the output of this sampling process. So I want some guarantees on the quality of the output. And we know very well that those generative models, they are able to do marvels, but they are absolutely not immune to making stupid mistakes. So, for example, here, I took this from an image paper where what they show is, okay, you can create a very nice looking image of a mountain lake where the reflection of the mountain on the lake is not consistent with the mountain. So, okay, I cannot do science with this. It's really a blatant error that is not acceptable. The second question you should have in mind is, okay, but wait, here, I want to use a generative model to sample, but actually this is a very different task from the generic task of generative modeling. In generative modeling, the input is an extensive dataset of realizations of X. I want to train ChatGPT. I need to scan the web with so many different examples of what's natural language. Now, in sampling, this is not my input. My input is a mathematical expression of the distribution I want to sample from. And precisely, the realizations is what I want to produce. I want to produce these realizations, but I want to produce them not from an extensive set of examples, but instead from the mathematical knowledge of the target distribution I want to sample. So, okay, so how do I go around those two obstacles as I try to use generative models for sampling? Well, the idea is that to be able to, what we're going to do is approximate the target distribution and post-process the samples. And actually, we are able to do that if we use a certain class of generative models that are called normalizing flows. So those normalizing flows, they are working along this paradigm of deep latent generative models. So I have my simple Bayes distribution from which I create outputs by putting them through a learnable neural network. But now what I impose on top of it is that actually my t theta is a diffeomorphism. So it's an invertible map. And if I do this, what I gain is that actually I can write down explicitly what's the expression of my rho theta of X, my effective density for on the outputs of the generative model is given by a so-called change of variable formula, where I need to evaluate the Bayes distribution at the inverse of the points. And then I have a Jacobian term that comes from transporting the sample from the output to the input, which is effectively an invertible change of variable. And so why is this a blessing? Well, because first, I can post-process easily the sample, in this case, of an approximate model for making them exact samples. So what I need to do is simply to revisit the two simple paradigms of sampling I presented first. So for example, importance sampling. If I have still my toy target distribution with my two worlds, and if I have access to an approximate model for this toy target, so this is my rho theta of X that I trained and that is approximately representing my targets, well, I can rewind the process of importance sampling. So I propose, but this time I propose with a very well adapted proposal that is my deep generative model. And then I reweight. And you can see that this time the proposal is much more adapted to the distribution we care about. And therefore we are going to be able to drastically lower the variance of the estimators this way. Similarly, what we can do is also revisit Markov chain algorithms, and in particular the Metropolis-Hastings algorithm, which is based on, from a proposal, having a criteria for accepting or rejecting this proposal. And okay, I'm not writing explicitly what it is here, but basically the idea is that I'm going to use this distribution as a proposal. Contrarily to traditional MCMC, my proposals are not going to be local. I'm not going to say, okay, I was there, so I'm trying to jump in the neighborhood. Here, at each iteration of the Markov chain, I just query the generative model, propose me something new. And if you do this, you're likely to see chains like this one, where you are going to independently go from left to right in the two worlds, and accept reject with a criteria that is going to be consistent with the law and ensure that you have, in the end, samples that are distributed exactly according to the target distribution. So in particular, you can see that the artifact in my model that is linking the two worlds that doesn't exist in my target is not visited because every proposal that has been made here has been rejected by the Metropolis Hastings acceptance criteria. And so I have an exact sampler that is helped by an inexact generative model. Okay. So now how do I train? So I need to train without data a priori. So there are different methods that people have seen. And so maybe something I forgot to say is that here I'm insisting on the fact that it needs to be a normalizing flow because you need to have the knowledge of this density in order to compute the weights. And you also need to have the knowledge of this density in order to compute the accept-reject criteria of the Metropolis Hastings. So how do you train? Well, an adaptive training is one option that you have. And the idea is that you're actually going to converge the training and the sampling all together. So you can imagine doing this in 3 steps. First, you run a local sampler like the one I showed at the very beginning of the talk. It has no information about the relative weight of the two modes, but it gives me some information of where there is high mass in the target distribution. I use this data to train with a classical generative modeling training objective that is maximum likelihood. And therefore, I'm creating a model that still doesn't have information about the relative weights of the two modes because it was not in the data, but starts having some relevant information about the target. And then once I have it, I can use my more sophisticated samplers, the ones that are assisted with the generative model, to recover the part of the information I didn't have, that was the relative weights of the two modes. And so in practice, I'm not converging this. I'm doing this machine learning style, meaning that I'm doing a few iterations of this, followed by a few iterations of gradient descent on this objective, a few iterations of this type of chains, and converging everything at once, which gives me a model that is trained progressively on better and better data with a chain that converges faster and faster as it has a better and better proposal kernel. So that's the idea. And this requires, unfortunately, the knowledge of the mode's location. That is to say that there is no such thing as a free lunch, where if I were to initialize my local sampler at the beginning as with only one of the location, then there is no reason for me to find a new mode with this approach. So depending on your application, you may be worried that you know the location of the modes or not. I will come back to it in the last minute I will have for the talk. But before, I wanted to tell you that for this adaptive training, there is a Python package I was involved in developing, so based on these former papers with collaborators, that was for which the leading effort for the implementation was made by Case Wang. It's written in JAX, that is just-in-time compilation compatible machine learning framework, and so it's quite fast. It even has a documentation, this package. It's not only pip installable, and it's been used actually mainly in the astrophysics community recently in the cases of Bayesian inference, and in particular for gravitational waves, inference of parameters. So now, if you don't know the mode location, there are some way to fix it. And in particular, what you can do is use another type of training objective, that is the so-called reverse Kullback-Leibler objective, where you can write it as something that is not an expectation over data, but that is an expectation over the model itself. So I don't have much, I don't have time left, so I'm not, or maybe I have 1 minute, wait, 2 minutes. So maybe I don't develop so much. Let me see. Well, okay, so maybe if I just finish on one additional idea. Overall, another idea that you can incorporate in this paradigm is the idea, again, of annealing, where the idea is that you can consider your target distribution and modify it in a way that it's going to become simpler. So typically, if you change its temperature, so you're thinking of the Gibbs-Boltzmann equivalent, and you're raising it to a power of beta that is smaller than the one you have for your target, what you can see is that, for example, my toy initial distribution can end up looking like this, so being easy if I raise a lot the temperature. While if I decrease the temperature, I can reach back my target distribution. And so this can be a true vector of managing to find modes, for example, when you don't know, by treating your problem sequentially, at first solving it at very high temperature, and then progressively lowering the temperature to find the modes of interest. So, okay, and so we have some recent work where we look at precisely which annealing rates you should use. I'm happy to discuss it offline if you're interested, but before just I conclude, I wanted to mention that, okay, if we take a step back and try to look at what's the state of affairs in enhancing sampling with normalizing flows, well, there's been proof of concepts of that are across physical domains. So in particular, in this idea that you want to sample from the Boltzmann distribution, I mean, ranging from biomolecules to quantum chromodynamics. But also, as we are developing these methods, we also understand what are the limits to this approach. And in particular, this approach starts to fail when the landscape is too complex or the dimension is too high. So typically, when I talk about complexity of the landscape, it can be when you look at strong repulsions in the molecular systems, these create very stiff landscapes that are very hard to sample. So, of course, there is a lot of research still to be done. And of course, I didn't have time in this 30 minutes to introduce you to the concept and develop what we are doing really nowadays in the research. But just to give you what are the directions we are currently working towards, the idea is to couple generative models with traditional enhanced sampling algorithms. So go beyond this important sampling of Metropolis Hastings and couple this with generative models. And we are also leveraging more powerful generative models that are the more recently introduced diffusion models or flow matchings that Florence introduced this morning. And so with this, I thank you very much for your attention.
Thank you very much, Marylou. Do we have questions in the room or on the Zoom? A question?
Thank you for the very interesting presentation. So you're saying at the end, concluding that it doesn't scale well with dimension. Can you give us a sense, like, does it scale well up to 100, 1,000, 10,000?
Yeah, that's of course, that's an excellent question. Off the shelf, something like 100, couple of hundred will work well, but this is always, I mean, there is always a caveat on how difficult is your landscape. If you want to sample a Gaussian distribution in 10,000 dimensions, you can do it. There is no problem with this method. So the question is a bit where the rest of the complexity, I mean, the geometrical complexity also lies. But if things are well behaved, you can go, several thousands. If things are starting to get a bit tricky, you can think more like a few hundreds, which is already quite non-trivial. Like, for example, for those gravitational wave example, it's like off the shelf.
Thank you very much.
Okay. Other questions? Yep.
Just an open question. So you say you're interested by multimodal a posteriori. So once you have the multimodal a posteriori, what do you do with it? Because when you have the MMSE, for instance, it's not always adapted. So sometimes it's very difficult to represent the result when you're in very high dimension. So I was wondering, okay, once you arrive to estimate your density in 1000 dimension, what do you do with it?
Yeah, so I mean sorry, stop sharing. I'm guessing then the idea is that what you need to do is to be able to post-process the samples. So for example, if you have no idea of the structure, I'm not sure what you can do. Okay, never mind. But if you just remember my initial example where you have two islands that you think are possible, then if you're able to sample, you're able to compare with which probability you're going towards one or towards one other. So it's just giving you a relative likelihood of the two. I mean, I guess there is an idea that you need to be able to cluster your representations and then make a choice between the clusters.